but I was looking at our schedule. I just graded your take-home quizzes earlier today, and I posted the grades, and we only have 3 quiz grades. So I want to get up to at least 9 or 10 so that I can drop 1 or 2 of them. And so so you're aware, we only have about 6 weeks left in the semester. So I plan to have at least 1 quiz a week from here on out. All right. So, and I plan on them all being from the homework. All right. So this will kind of keep you honest, but this also means you need to keep up with the homework. Make sure that you're doing it. You know, whatever we cover the class before, that should be done before you come to class. And you know, any questions you might have over that, get with me, get it to the tutoring lab. All right? You want to talk about the quiz? Yeah. Okay. So let's do, and I am recording. My microphone is on. All right. So the first one was y equals the natural log of sine squared x. And so this is a summary of really like the 4 formulas we had from last class. And you'll be looking here at the second one. We're trying to look at the natural log of something, right? And we're trying to take its derivative. So the derivative of this will be 1 over u, which u is whatever's inside the log function. So it's 1 over what? 1 over sine squared x. But then times, now you have to take derivative of what's in here. And that's going to be chain rule, because you've got sine x but then squared. So that's really like sine x squared, right? So to take the derivative of this, the 2 has to come out first. So 2, then sine to the first power, right? And then what? Times cosine of x. I mean, that's the raw derivative. You could then like cancel a sine if you want. And then you could have like 2 cosine x over sine x. But that's really just 2 cotangent x. I'm wanting to see this the most, especially if I'm only giving you a few minutes. But this is the cleaned up version of that. All right, so the second one is the square root of x times e to the x. So to take the derivative of this, we have to use what? The product rule, right? This is a product right there. You have multiplication, so you have to do derivative of the first one times the second plus derivative of the second one times the first one. So the derivative of this one first is just 1 over 2 root x, and then times the second one. Then plus, now what is the derivative of e to the x? It should just be itself, e to the x. So e to the x, and then times the first one. That's it. Now the last one, the bonus, this one's a little more involved, but start out with this log function. And you're given a point. And you're asked to find the equation of the tangent line to that curve at that point. So the first thing we need to do is find the derivative. So the derivative of this, again, you have natural log of u. So the derivative of natural log of u is 1 over u, right? X squared minus 3x plus 1. And then times the derivative of what's in here, which is what? 2x minus 3. That needs to be in parentheses. So you could, if you want, slide that on top. Okay, so that's your derivative, right? So if I actually plug an x value into this, it will give me the slope of the tangent line at that point, x. And I'm interested in what's happening when x is 3, right? So at 3, the slope of the tangent line is equal to whatever I get when I plug 3 into this. So let's see, 3 here, we get 6. Take away 3, we get 3 on top. And then what happens here if we plug in? We get 1. So your slope is 3. All right? That's not the answer. Okay, that's just the slope of the tangent line. We want the equation of the tangent line. So now you have to go back to this good old formula, y minus y1 equals m times x minus x1. And you have all this stuff, right? Y minus what? 0 equals m. M we just got was 3. And then x minus 3. So this turns out to be y equals 3x minus 9. That's the equation of the tangent line. Okay, so don't be all freaked out or anything. It's, you know, I just want you all to be prepared now. Like, we've been pretty laid back in here as far as quizzes, but yeah. Y'all all right? Okay. Also, make sure you're here on time, because, you know, if we start the quiz, I'm going to start it at the beginning of class. So if you miss it, you miss it. Or if you come in late, you're only going to have a few minutes. Okay, so let's look, just so we're clear. Last class, you know, sometimes there's lectures that just want to flush them and wish they never happened. That's kind of like last class. So let's just review real quick the main ideas. If we ever have e to something, the derivative of that is itself, e to that something, but then you always have to do chain rule, derivative of what's up here. Natural log of something, same thing. The derivative is always just 1 over that something, right? 1 over the u, but then you always have to multiply by the derivative of what's inside. Now, these two formulas are the same things, but for the non-special case. So this is the special case where your base is e. E to the u, and then here, natural log is log base e. So if those bases are different, and you have, let's say, like 5 to something, the derivative would be 5 to something, and then times the derivative of what's up here. And then log base a of something, it's going to be 1 over u. And then this part right here is the special little thing you have to throw in there. Natural log of the base. And then chain rule says times the derivative of what was in here. So those are the kind of 4 main ideas from last time. Yes?
So what's the difference between the first and the third one?
The first and the third one. Because the top one is e. That's a very special, e is a number, right? A specific number. This is the formula for any base, as long as the base here is bigger than 0 and not 1. So this is the formula you would use if you had like 4 to the x.
Because I got confused and I put that as for the quiz. I used that one.
Use this one? Wait, hold on. I'm missing something in my damn formula. Okay, it's not, yeah, I'm missing my ln here. Sorry. This is ln. Then times u prime. But if you did this formula the way I had it written down, you should have gotten it right still. Yeah.
So is that, yeah. Okay.
Because the reason why this formula will work for that is because when you get to natural log of e, the natural log of e is 1. So that goes away. Okay. All right, now we are not done with this section. We had started doing this thing called logarithmic differentiation towards the end of class. And so I want to do another one of those problems. Let's take a look at something like this. Let's say we have y equals x squared plus 2, let's say to the 8th. And then let's say we have x to the 4th minus 3x, let's say to the 12th power. And let's say we want to find the derivative of this. So to find the derivative of this would not be that fun. I mean, we would have a product rule here, wouldn't we? Wouldn't that be a product right there?
Yeah.
So then you would have derivative of this times this plus the derivative of this times this. And when you do this one, that derivative, you got to do some chain rule, don't you? So I mean, it could be done. Let's not say it couldn't be, but we're going to do this using logarithmic differentiation instead, just to see how the logarithmic differentiation allows us to kind of make this a little easier on ourselves. So do y'all remember the first step for doing logarithmic differentiation? You do natural log on both sides. Okay, so I do natural log of y here. That's natural log of the left side. And then natural log, I'm going to do a big parenthesis here, and then x squared plus 2 to the 8th, and then x to the 4th minus 3x to the 12th. All right, so we took natural log on both sides. Now what does that allow me to do now on the right side?
Bring the 8 over and the 12 over.
Bring the 8 and the 12 out? Can I do that? Yes, you can, but not yet. Okay, not yet. First, you have to use the fact that you have two things being multiplied, right? It's like this times that. Those two things are being multiplied inside of a log, aren't they? So I'm going to split it into two logs first. See, the problem is if you bring the 8 out and then the 12 out, what are you going to do? Like 8 times 12? It doesn't work because you have two pieces in here. If it was one piece like that, then you could drop the 8 out. Okay, so my first step after the natural log is to split this into two logs. And when I say split into two, what's going to be the operation between the two? Plus, and that's because this was multiplication, right? So plus natural log, and then I have x to the 4th minus 3x all to the 12th power. Now you can pull the powers out on each of those. Okay, so the 8 can come out and the 12 can come out, and that is just a property of logs. So natural log of y equals 8 natural log of x squared plus 2, and then plus 12 natural log of x to the 4th minus 3x. Are we good up to that point? Okay, next thing. What? Do we need to do any more algebra? Can you take this log with the two things inside, can you split that into two? No, you cannot, because this is addition, right? It only works with multiplication. So you can't simplify this anymore. And you can't pull that 2 out, because the 2 would have to be on both of these things. So this is pretty much as far as we can go. And here, same thing. Can't split this into 2 because it's subtraction. So now is the point that we will take the derivative. All right, we're going to do implicit differentiation. So what is the derivative of the left side?
It's 1 over
1 over y
then
times y prime. Okay, so we did that last class. This is the chain rule. It's this formula right here. Okay, we're saying what's the derivative of natural log of something? Well, it's 1 over that something times the derivative of the something. So derivative of natural log of y is 1 over y times the derivative of y, which is not 1. It's y prime, right? This is really like dy dx right here. And then equals over here, I have 8 times this, right? So 8 will come for the ride. Okay, what is derivative of natural log of something? 1 over that something. Okay, times what? The derivative of the something, which is 2x. And that 2x will go on top after I'm done here. And then plus, let's see, 12 comes for the ride because it's multiplied. And then I have natural log of something again. So 1 over x to the 4th minus 3x times derivative of what's inside. What is it? 4x cubed minus 3, right? And I have to have that in parentheses. So that's the derivative of what was inside the log. So let's try and clean this up a little bit. 1 over y prime equals, I'm going to put the 2x on top of this, and I'm going to put the 8 there with it. So I'm going to get 16x over x plus 2. Plus, let's see here. I'll just put this up here, and I'll put the 12 up there with it. 12, 4x cubed minus 3 over x to the 4th minus 3x. Any questions? Are we done? We are not done. We have this one last step, which kind of sucks. We have to multiply both sides here by y so that these y's will cancel, and we'll get y prime by itself. So if I multiply y there, I have to multiply this entire side, right, by y also. And that will give me my final answer. It's going to be ugly, but here it is. So we have y prime, that's this, equals all of this crap in parentheses, 16x over x squared plus 2 plus 12 times 4x cubed minus 3 over x to the fourth minus 3x. But now I multiply that times y, right? And what is y? It's the original equation, right? It's this. So I need to slap that out here. X squared plus 2 to the 8th, x to the fourth minus 3x to the 12th. That's your derivative. Yes?
Would you leave it like that, or would you put a big parentheses on it?
You put a what?
Put a big parentheses around the whole thing?
Around like this whole thing?
No,
Oh, this right here?
yes.
You don't need to because this is multiplication. If we were to try and clean this up, we could take this whole thing and distribute it through to there, and then this whole thing would go to here. Right, that's about all we could do. In fact, why don't we do it? Let me show you what this next line would be. Well, I'm missing something. Man. Hold on. To what power? 11. Okay, so y'all see what I did here. When this went to here, right, this x plus 2 to the 8th and this x plus 2 to the first power cancels out one factor, which is why when I bring this over to this one, I now have x plus 2 to the 7th. And I still have this piece sitting next to it, and I still have the 16x. That's 3 things I've done wrong today already. I think I may need to go out and come back in. All right, so how about here to here? We got the 12, we've got this, and then x squared plus 2 to the 8th, nothing cancels, so that's here. When I do this one over that one down there, one of them cancels, so I get to the 11th. All right, the important thing here is to see that we can use this thing called logarithmic differentiation in a problem like this. By taking the log on both sides, we can split this into 2, and then the powers come down, right? Then we differentiate. So there are a few problems in your homework that are similar to this. So make sure you work those out. Let's do one more. One more out of this section. Y'all seem all doom and gloom now. Y'all all right? Okay. X squared y equals x plus y. Find y prime. All right, so we are trying to find y prime. The problem that we have with this equation is that we cannot solve it explicitly for y. You can't get y isolated by itself. And we've had this happen in the past. And do you remember what we did when we couldn't solve for the variable y? It brought like a whole new category of equations. Do you remember what we called it? Implicit differentiation. That's what we're going to do here. We're basically going to take the derivative on both sides with respect to x right now. So let's see what would happen if I take the derivative with respect to x. So I'll write this down just so you know it. I'm taking the derivative with respect to x on the left side equals, now I'm taking the derivative with respect to x on the right side. So just remember, we're doing it with respect to x. So anytime we see x and we take its derivative, we get 1. But when we take derivative of y, we get dy dx, or I'll just call it y prime. All right? All right, so let's take derivative of this. How do you take derivative of e raised to something? What is the derivative of e raised to something? E to that something first, right? E raised to that something. But then chain rule says times the derivative of the something, right? Now, what's the derivative of what's up here? We're trying to take derivative of this, right? You have a product rule there, don't you? You have x squared times y. So I need to do times, in parentheses, I need to run a product rule on this. So what is the derivative of this using product rule? 2xy plus, so you've got to go derivative of this times this now, right? What's derivative of y? With respect to x. dy dx, right? dy dx times x squared. Okay, that is your product rule on the exponent part of the exponential functions. So do you all see that this is e to the u prime from the formula? E to the u prime. U prime happens to be a product rule. We are done on the left. How about on the right side? Derivative of these two, we can do them separately because there's addition. So what's the derivative of x with respect to x? 1 plus what's the derivative of y with respect to x? dy dx or y prime. So just remember, y prime means dy dx. That's what it's meant this whole time. So if I'm trying to find dy dx, what would I have to do now? Yeah, we have to isolate dy dx. We have to get all the dy dx stuff on one side, all the stuff that's not dy dx on the other side. But there's a problem because this dy dx is trapped inside this parentheses, right? Which means first I have to distribute this e to the x squared y through. So here's what this will look like. How do I want to do this? X squared e to the x squared y. I'm going to replace my dy dx with y prime. Is that all right with you? Okay, equals 1 plus y prime. So do you all see that when I distribute this to this, I just slap these out in front of it? And then when I distribute this to this, I just put the x squared out in front of it, and then I just left the y prime in the back. And now let's take all our y primes to one side, and everything that is not y prime to the other. So I'm going to leave this one here. I'm going to bring this y prime to the left. I'm going to leave this 1 here, and I'm going to move this thing to the other side. Okay, y'all see all the algebra in that? It's just moving things around. Now, why do I do that? Why did I do that? What's the point? I can factor out y prime on the left. So factor y prime out. When you do that, in parentheses, you're going to have x squared e to the x squared y, then minus 1, and then equals 1 minus 2xy e to the x squared y. Last step. Divide. Is that what I heard? There it is. So for this, we used implicit differentiation. The problem before this, we used what? Logarithmic differentiation. The difference between the two methods is that in this one, we could not solve for y, right? So we just implicit differentiation through both sides. On the previous problem, it was already solved for y, right? So why did we bring in the logs? On the previous problem, why did we bring log in on both sides? So we could break it up, right? So there's a major difference between when you use the two methods, and you need to be able to recognize that. All right, so in your homework, you will have a problem like this one. This was actually number 61. In the homework, you're supposed to do number 62. And they give you an implicit equation, and they ask you to find the equation of the tangent line at a point. So imagine I just did one more thing here. Let's say that I gave you a point, like the point 1, 0. Let me just check that it works. Yeah, 1, 0 does live on that curve. So if I wanted the equation of the tangent line at that point, what would you do at this point? You take 1 and 0 and plug them in where? Into this, right? 1 for x, 0 for y. And when you plug it in here, what does that give you? The slope of the tangent line. So that would give you m. And then you use the equation y minus y1 equals m times x minus x1, and you have your equation. So just like the quiz problem. All right, let's move on. Next section. So last section was all about, hey, let's talk about the derivatives of exponentials and logs, right? And now this next section, we're going to talk about another category of functions that we have steered clear of. And those are your inverse trigonometric functions. Now, I'm not going to go into a lot of detail, but I do want to give you a little bit of detail, just a little bit. So recall, that means I'm asking you to think from back in pre-cal, which was ages ago, right? If someone were to define a function f of x equals sine of x, uh-oh, all right? No, I'm just kidding. Are those the erasable ones? No, okay. If we define a function f of x equals sine of x in pre-cal, we graph it, looks like this, right? And in pre-cal, we would say that this is a function, right? It's a function because it passes the vertical line test. Now, does that function have an inverse? Well, yes and no. I mean, if we look at it right here, the way it is presented to us, it won't have an inverse because it fails the horizontal line test. That's the test for inverses. So if you remember back in pre-cal, what we had to do was we had to cut this function. We had to stop it at pi over 2 and then go backwards to negative pi over 2. And if we just look at our graph between here and here, so if we restrict our domain, so if we just look at the sine function on the interval negative pi over 2 to pi over 2 and erase everything else, then that piece right there is a function, passes the vertical line test, does have an inverse because it passes the horizontal line test, right? Just that little piece. Not only that, it includes the entire range. So this is -1 down here, and this is +1 right here. So it includes every number between -1 and 1. So we couldn't just cut that piece because that wouldn't include the whole range, right? So we cut just enough to get the whole range, but still satisfy vertical and horizontal line test. So once we do this, then we define the inverse function of that function to be, and this is the way we wrote it, arcsine of x. Okay, so this arcsine function undoes that function. Whatever this one does, this one undoes it. So like this, if I say, hey everyone, what is sine? Let me ask you, what is sine of pi over 4? Everyone in here would be like, oh yeah, that's just root 2 over 2. Okay, so that's your unit circle going to pi over 4 and looking at the, which coordinate? If I'm doing sine, what is it, the x or the y coordinate? The y coordinate. Okay, so you're looking at the unit circle, you're going to pi over 4, you're looking at that point that you all have memorized, and the y coordinate is root 2 over 2. So sine of pi over 4 is root 2 over 2. Now, if I ask you what is arcsine of root 2 over 2, your answer will be pi over 4, right? So the inverse sine function undoes the sine function. It takes this thing back to where it came from, right? Does that all look kind of familiar to you? All right. There is a domain on this one. The domain here is you can only plug in numbers in between -1 and 1. And that should make sense because the inverse sine function is taking the outputs of the sine function, these numbers, and it's taking them back somewhere, right? But the sine function only spits out numbers between -1 and 1. So this thing should only be able to handle things between -1 and 1. So if you go on your calculator and you were to type in arcsine of 2, you would get an error, right? Because this 2 never comes out of the sine function, so I can't tell you what angle to go to, right? All right, so that is your kind of recap of what the inverse trig function is. And we do that for cosine. We do something similar, and we do it for tangent, we do it for cotangent, we do it for secant, we do it for cosecant. So all 6 trig functions have inverse functions. All 6 trig functions have domain restrictions, and they aren't the same for each one. Do I remember how we have to restrict cosine if we want to have an inverse? It's not -pi over 2 to pi over 2. What is it? 0 to pi. That's for cosine. And then for tangent, it's actually the same thing. So again, I'm not going to review all this, but that doesn't mean you shouldn't. All right? You should go back and take a look at it. All right, so if this is a function, right? If this is a function, there is a graph to it. Let's take a look at the graph. We may as well. I'll go to my trusty Desmos. And I'm not sure how you type it in. Arcsine, I think it'll handle that. There we go. Arcsine x. And why don't I, below it, put sine x. And let me do that on -pi over 2 to pi over 2. Oh, whoa, what happened? What? Why is it not wanting that? Oh, yeah. Bracket. Bracket? This thing is smarter than me. That's going to do it. There we go. All right. So can you all see this well enough? The blue piece, right? This blue piece is that sine piece, right? And then this red curve is the arcsine. That's its inverse function. And do you remember this property of inverse functions, that they are reflections of one another over this diagonal? That whenever you have a function, if it has an inverse, then when you graph it, it's the reflection of itself over that diagonal. You all remember that from somewhere in college algebra? Okay, so that's why it looks like that. It has to. So if we have this new function, arcsine, right? This one right here, then what's the slope of the tangent line there? Right? We need to be able to take the derivative of that. So we need to know what the derivative of the arcsine function is. So that's what this next section is about. It's about, hey, look, everyone, we have these six inverse trigonometric functions from pre-cal. What are the derivatives of each one of them? All right? So we're gonna prove the first one. I'm gonna prove the first one, and then after I prove the first one, I'm gonna just tell you what the next 5 are. I'm not gonna go through the proof for each one. All right? So let's start with this. If y equals arcsine of x, I would like for us to find y prime. So the problem is, if I'm asking you to find the derivative of arcsine of x, this is not chain rule, everyone. This is not chain rule. -1 does not come out, because -1 doesn't mean raised to the -1. It means inverse. This is one of the few times in math where our notation just sucks, all right? It sucks. That's why sometimes you'll see it written this way, arcsine of x, because that way you're not confusing that little negative exponent. So if we're asking what is the derivative of this, right now we just don't know, right? And you can't go look at your formulas and be like, oh, it's this, because the whole point is, where did that formula come from? So here's how we're going to do it. Check this out. This is pretty nice, actually. Okay, watch what I do. You just tell me what I'm doing. What'd I do? I took sine on both sides. So it's not multiplication because sine, S-I-N, is not a number. So basically I took the equation, I took sine on both sides. All right? Y'all agree? What does the right-hand side turn into? Just x. Because you're plugging x into the inverse function and then plugging it into the sine function. These two functions undo each other, don't they? So it's like x goes into this, something happens, then that answer goes into that, and it should go back to x. So the right-hand side should turn into x. You with me? Now what I'm going to do is I'm going to take the derivative implicitly with respect to x. And the reason I'm okay taking the derivative now is because I know the derivative of sine. So let's take the derivative with respect to x on the left and the derivative with respect to x on the right. It's stick time. And this is not the right class. There we go. Okay. Surprised none of you have gone and stolen these sticks and thrown them away yet. Franklin, where's Franklin? I haven't seen him in a while. Hope he's all right. Luis, how's it going? Ready for the game tonight? I don't know what I'm talking about. I'm just messing with you. Okay. Derivative of this. So what's derivative of sine of something?
Cosine.
Cosine of that something, right? Now, are you done?
No.
What do I need now?
The
Derivative of y. So what is derivative of y with respect to x?
dy.
dy dx, right? Which I'm going to call y prime. That all right, everyone?
Yes.
Okay. Now, you're on a roll, man. Derivative of this?
1.
1. Okay, great. Now we can solve for y prime, can't we? Let's solve for y prime. So y prime, I get 1 over cosine of y, don't I? And what is 1 over cosine by definition? It's secant, right? So we're really getting y prime is equal to secant of y. Y'all with me? That was pretty straightforward, right? That worked out pretty nice. Okay, now this is not the formula you're going to find in your book or in your notes. And the reason why is because right now, the derivative of y, we actually need to know what y is, right? I would like for this to be an expression that has x in it instead of this, all right? You all okay? So check this out. I'm going to go back and I'm going to do something right now that, oh, here it is, right here. You see that? You see that right there? That equation right there tells me a lot of information, a whole lot. I'm about to draw something for you. It's a right triangle, okay? I'm going to call this angle right here y. And then I'm going to put x here and 1 here. Now, look at this triangle. Do you agree that this triangle matches that statement? So look at this right here as really saying that sine of y is x over 1, because x is x over 1, isn't it? And sine, by definition, back in pre-cal, on a right triangle, sine is opposite over hypotenuse. So when I say sine of the angle y is equal to opposite over hypotenuse, that means when I draw a right triangle, if I make the opposite side x and the hypotenuse 1, this triangle matches that equation, right? Yes? This right here is what we call a reference triangle. It's basically a triangle that we are going to use. We're using an equation. We are going to use that equation to draw a triangle, and we are now going to reference this triangle to get all the information we need about this right here. We would like to know what secant y is, right? Secant of y. What is secant of y? Well, it's hypotenuse over adjacent, right? Hypotenuse over adjacent. So if I knew what this side was, I would be able to replace this, right? So can you tell me what that side is? Yes, you can. You can come, let's call that side just for now, let's just call it A, all right? So what can you tell me about A? Can you solve for A somehow? Yeah, you could go A squared plus x squared is 1 squared, right? Pythagorean. And then A squared is 1 minus x squared. And that means A is equal to plus or minus square root of 1 minus x squared. So that's just your Pythagorean, right? And I'm only going to look at the positive answer here because A has to be a positive number, right? A is positive here. It's the length of a side of a triangle. So this side right here is actually this. How many of you have to take Cal 2? Okay? All day long we do reference triangles. All day long. I mean, this is just, we just do it. We just part of, it's like 1 plus 1 to us in Cal 2. We just do it all the time. All right? So get used to this idea. All right. Well, what's secant y then? We said it was this over this, right? And now if I just replace that, 1 over square root of 1 minus x squared, I now have a formula for the derivative, don't I? And it has x in it instead of y. So to recap, if we wanted to find the derivative of the inverse trig function, inverse sine function, first thing I did was took sine on both sides, right? Then I differentiated implicitly with respect to x. Once I did that, y prime pops out, but this over here has something with y in it. I go back to the original statement here, I draw a reference triangle, I solve for the side I don't know, and then I come back and use that to get the answer. You can do that for all 6 inverse trig functions. Cosine inverse, tangent inverse, secant inverse, cosecant inverse, all of them can be done similarly. And when you do that work, you will come up with the 6 formulas. And now I'm going to just show you what they are. On your formula sheets, you should find them, look at them, introduce yourself to them. But here they are. Here's the first 3. So that's the one we just came up with that formula on our own, didn't we? Okay, look at the difference between that one and this one. Derivative of arc cosine of x is that same formula, but a negative. Okay? The derivative of arctangent of x is 1 over 1 plus x squared. There is no square root here. You see that? And it's a plus instead of a minus. This one right here, you're going to have dreams about that one in Cal 2. All right? This is super important in Cal 2, this one right here. The next 3, not as important. They really don't come up very often. All right? So here they are. Those are the next 3. So you don't have to memorize these 3. All right? And the ones before, I would say it's not super urgent that you memorize those 3. You definitely should get the arctangent one kind of burned in as soon as possible, just because in Cal 2 you want to be very familiar with it. Understand? Okay, now let's do some examples, because now that we have a formula, right, this means that everything that we've learned is in play. Chain rule, everything, product rule, all that can now happen with these. So we'll start with this one. Let's go something simple. How about if we're trying to find no. Okay, how about that? I want us to find the derivative of this. So on your formula sheet, who has their formula sheets with them handy? Okay, I'm going to look at this real quick because I want to write it the way it's written here. This is actually formula 19. So on your formula sheet it says d dx arcsine of x equals, and I need glasses. I'm very depressed about it. I'm starting to not be able to read up close anymore. I was underneath my daughter's car last night trying to change her oil filter, and I couldn't. You know, has anyone changed their own oil? You know, when you do the filter, you get it to where it just seats, and then you have to turn it a certain amount, and it usually says on it like, you know, quarter turn, half turn, three-quarter turn. So I'm sitting there, I'm looking at the filter, I could not frickin' read the damn thing. So I had to like take a picture and then like zoom in on the picture to be able to read it. Sad. Yeah, at least I have that, but still, my hands were all dirty and I was messing with my phone. All right, so this formula, the way that I want you to always remember every formula on those sheets is that really what's happening here is that if you have arcsine of anything, okay, let's not even talk about x anymore, just arcsine of something, that the derivative of that should be what? Let's see if you can follow, you know, how chain rule works with all these. 1 over square root of 1 minus that something squared, but then what? Times the derivative of what's in here. So you're always going to have that u prime sticking off the end. That's your chain rule. In all of these formulas, it's there. On your formula sheet, it doesn't write it that way, right? I guess it just kind of, I guess they assume that you understand that chain rule applies. But really, there's like a little x prime out here, which would be 1, right? But what if that's not x, right? What if that's 1 minus x squared? See, so this is the more general formula for it. So what is this derivative? 1 over square root of, so, sorry, not, I'm looking at the formula, 1, right? 1 minus what's here, right? So in parentheses, 1 minus x squared is in there. Right? Does everyone see that? That's 1 over the square root of 1 minus, or sorry, 1 minus u squared. There, I forgot to square it. Right? And then times the derivative of what's up here, which is negative 2x. With me? All right. This would be negative 2x over the square root of 1 minus. Now let's actually square that. If you take this and square it, you're going to get 1 minus 2x plus x squared. That's what would happen if you square it. But you still have this minus sign out here that has to distribute through to all those, right? Let's go ahead and distribute the minus sign through. And what? It'll be 1 minus 1 plus 2x minus x squared. That's what will happen when I distribute the minus. Then ones will go away. So all I get on the bottom is square root of 2x minus x squared. Right? Okay. That is the derivative of arcsine of 1 minus x squared.
Sir,
Yes.
that will be x to the power 4, right?
Pardon? Oh, did I not? Oh my God. Jeez. I'm trying to make excuses for why I'm making this many mistakes. I think I'm just stressed out right now. I think I'm stressed out. My dad's having a major surgery tomorrow morning. I mean, it's not like life-threatening, but it's a surgery no one would want to have. And then you know, like I can't be there because I've got to give my internet midterms to like 100 students tomorrow morning, and I think I have too much on my mind. I'm making excuses. There's no excuse for this. There's none.
I mean, you're only
Yeah, I know, but this is not, even when I'm stressed out, I don't make this sort of mistake. I'm ashamed of myself right now. That's squared, and that's to the fourth. Thank you. Y'all, I need y'all to like stay on top of me here today. This is squared into the fourth. I've told you about that vision I have, like when I die, I'm going to be in like math hell. Have I told you all about that? I just picture myself being tortured for all these mistakes that I made in class. Remember this? Remember when you did that? And I deserve it. I deserve it. It's a big, you know, I'm okay. I'll pay the price. So I deserve some lashings for that. All right, that's the derivative. Let's look at another one. Tell you what, man. Let's do some arctan in here. Let's get some arctan. Let's go x squared arctan of x. Let's find the derivative of this. Let's see if I can even do it. I don't even know if I can do it anymore. I'm losing my confidence here. All right, the derivative of this is, you know what I can do so I don't make mistakes? I can let y'all make the mistakes. I'm just messing with you. Brian, you're up. Okay, so Brian, what do you see here, Brian? Product, good. Okay, so we see a product rule here. There it is. Okay, so you're going to go one at a time here. So derivative of x squared, right, which is 2x, and then just times what? Tan inverse of x, right? Okay, so that's the first piece. Then what comes next, Brian? What's the next thing I write? Or tangent, right? Now I need a plus between them, right? So plus is next. And then derivative of arctan, so you go to your formulas or you've already got it memorized. It's 1 over 1 plus whatever's in here squared, which is just x squared, right? And we normally would have to do the chain rule here. We would then say what's the derivative of in here. But that's just 1, right? So there really isn't anything that pops out here. But we still have something else out there, right? X squared. So times x squared. All right, there we go. Not much cleaning up I can do here, all right? Right, like that? That's about all I can do. I cannot do that, right? No, cannot do that. If I do it, like a bolt of lightning will come hit me. It should. That's what should happen. All right, there's our derivative. Let's try something else. Ooh, that's nasty. Ooh, I like that one. That one looks nice. Okay, how about this one? Cosine inverse. This will be extremely interesting to see what happens here. Cosine inverse of sine inverse of x, and it's Marissa. Marissa, how you doing? That's you, right? Okay. What do you see? Do you see product? Do you see quotient? Do you see, I'm like, when you look at that, chain rule, okay? So you always start with the outside function, right? Which would be arc cosine. All right, so what is the derivative, Marissa, of arc cosine of something? Negative 1 minus x squared, right, in the formula, but or do we have x in here? Sine x squared. So check that out, sine x squared. Do y'all see that? Okay, because it's not x inside, it's sine x inside. Now, Marissa, are we done? No. What do we need next? The derivative of what's in here, right? Which is cosine x. Right? What? There's something really weird happening here. Do y'all recognize this right here? What is that? That's cosine squared x, isn't it? 1 minus sine squared x is cosine squared x. So this is really like negative 1 over the square root of cosine squared x, but then times cosine x again, right? And when you do the square root and square, these cancel, right? And so you're really just getting like negative 1. What? That makes no sense. Does it make any sense? Something's weird here. Because look, if I came in here today and I said, hey, look, the derivative of something is negative 1. What is it? What would you tell me? Take the derivative of something and you get negative 1. What is the function? Not negative 1. That's negative x, right? Take the derivative of negative x, what do you get? Negative 1, right? We're getting negative 1 as an answer, which means if the derivative of something is negative 1, that means that should have just been x? How is that even possible? Because it's not. It's like cosine inverse of sine x, right? How is that x? So maybe we can do something here. Let's do this. Let's just take a look at this expression real fast. Let's call this right here, just for the sake of it, let's call it m. All right? All right? Now, I'm going to write something down. Sine of x is m, everyone. All right? Wherever you see sine x, I want to replace it with m. By the way, we're done. Okay, this is the answer, but I'm having us consider something right now. So if sine of x is m, do you agree with this? Just tell me if you agree with this or not. Does that picture go with that? Yes? All right. What is this side? Square root of 1 minus m squared, right? Okay. So now let's see what this is saying. What is cosine? We want to know what cosine inverse of m is, right? What is cosine inverse of m? It's something, right? It's something? I don't know. I want to call it something. Let's call it y, because that's what it is up here, okay? Let's call it y. Then what is that? Cosine inverse of m. Trying to get you to think of what cosine inverse of m means. I don't know if I'm able to stretch this far or not. What's cosine inverse of 1?
1
Pi halves, is it cosine inverse? You're on the right track, but it's not pi over 2. Isn't this saying at what angle is cosine 1?